So this lecture in the wave nature of light is on Newton's rings and air wedges, and this is from section 10.1 of your textbook, specifically at the subheading Newton's rings and air wedges. That shows up on page 508. So we'll get into this, and the first phenomena we'll talk about is Newton's rings, and this is a phenomena that occurs when we have a curved glass surface on top of a smooth glass surface. So what basically happens is when the curved glass is placed on top of the flat glass surface, and we have monochromatic light that illuminates it, we start to see these concentric circles that show up, and this is called Newton's rings. And they basically come up because of the interference between the rays reflected by the top and the bottom of that little air gap that appears. So you can see in the image A there's a small little air gap near where the curve of the glass is and where the point of contact is between the curved glass and the flat glass. So at that point, we start having phase differences, slight phase differences that end up dispersing the light, and basically it creates this pattern that you see in B. One of the applications of this is to test imperfections in lenses. So if we have perfectly spherical lenses, the Newton's rings pattern that we would see would be symmetrical. But, and you can see that example in the picture A. But if we have lenses that are slightly deformed or defective, you would see an irregular pattern like you see in B. So what I'm going to do now, I'm just going to do a little sample or not a sample, but a demonstration. So what I have here is two slides that you probably use in a biology lab. But if they're both flat, if I place them on top of each other, though, and usually I do this with students and I give physical examples, but you can kind of feel that they sort of stick together a bit. And really what's happening is an air gap is being created because they're so flat, and it's hard for air to escape when we kind of place one on top of the other quickly. So it creates a little bit of an air gap. And that little air gap actually makes it so that there is only a few contact points between the glass, the one flat glass and the other flat glass. So what I'm going to try to do is create an air gap that will give me a Newton's rings pattern. This will not be a perfectly symmetrical one because it will be touching at various points, so we'll see an imperfect Newton's rings phenomena. But let me see here. If I place this on top, might take a little bit of time. Actually, I got it right here. So what I'm seeing is a Newton's rings pattern, and in order for you to see it, I have to tilt it a little bit. Actually, I'll use my hand here to block that. So very, very faint, but what you could see, and I'll put some labels on the screen there, is a Newton's rings pattern that's appearing on this on these two slides. So if I tilt it, I could see it better. That's why I've tilted it for the camera here. So that's what the phenomena Newton's rings is. And in this case, I made it occur by having two flat surfaces, but because of an air gap that I created, the flat surfaces did not have, there were some points where the two surfaces were not in contact because air was actually in between. And that gave us that irregular Newton's rings pattern, although it was somewhat regular, so it looks like the air gap was concentrated at one specific point. So going back to our slides here, I'd like you to copy this down. This basically explains what Newton's rings are. It's an interference pattern that shows up of concentric rings. And this occurs when light reflects from both the upper surface of the flat glass and the lower surface of the curved glass. And it's used to check lenses for imperfections. Now, we're going to talk about another phenomena that occurs with air wedges. And this is sort of similar to what I was doing earlier with the two slides. If we have two flat glass surfaces, and we start to kind of close them together, we actually create a little bit of a wedge, and we call it an air wedge. So the air, or I guess that little triangle that's formed by the air and the glass there, we can analyze that geometrically, and what we'll see is an interference pattern that basically it produces dark and bright fringes, similar to what we would see with Thomas Young's double slit experiment. But in this case, these air wedges are actually used to measure things that are very, very small. So an example is if you wanted to measure the thickness of a paper, you can place a paper between an air wedge, and it'll create a small little triangle. And then by analyzing the interference pattern of the light, we'll end up seeing these fringes. We can actually determine how thick that paper is. So you see that distance from E to D is the thickness of the air wedge. And if there was a paper that was inside this air wedge, it would be creating that triangle with that T thickness. And while it is at a little bit of an angle, we treat it as if it's perpendicular to the bottom glass. So I hope I explained that well enough. It's also covered on page 509 in your textbook, but let's look now at the geometry of this. So using similar triangles, we can see that ABG, the triangle, is similar to ACF. And ABG, the distance from B to G would be half a wavelength. The distance from C to F would be a full wavelength. This is where our fringes would occur. So you'd have a dark fringe. A first dark fringe would occur at lambda over 2. The second dark fringe occurs at lambda. Subsequent fringes occur at different values of lambda over 2. So we'd have 1.5 lambda, 2 lambda, 2.5 lambda, and so on. And by analyzing this, we end up with a relationship for the air wedge, and it's that delta x, that separation between the fringes, equals the length of the air wedge, where the length is basically the distance from the tip of that triangle, or where the air wedge originates, to the point where we measure our thickness. So if it was a paper that was in between, the air wedge length would be how long until we actually get to that paper that's inside the air wedge. Lambda is the wavelength of light, and T is the thickness of the air wedge. So let's look at a question and see if we can solve this. It says a sheet of paper that is 0.12 millimeters thick separates two microscope slides. So the two microscope slides, like I was doing with my Newton's rings example, those two slides, if we put them together as like an air wedge and we put a paper between them, then we can end up using that as an air wedge. So we have this 0.12 millimeter thick paper that is separating these two slides that are 11 centimeters long. So that's the length. We're asked, what is the spacing of the dark fringes in the interference pattern when the air wedge is illuminated with red light of wavelength 660 nanometers. Okay, so in order to solve this, what I'll need to do is I'll write down my air wedge equation. Delta x equals L lambda over 2t, which is our thickness. And I will then start to substitute. I'm looking for the separation between the slits, so that's the delta x. My L is the length of those two slides, which is 0.11 or 11 centimeters. My lambda was 660 times 10 to the negative 9. That's my wavelength of the light. I'm dividing by 2, and my thickness is 0.12 millimeters. That's to the 3. So putting this in my calculator, I end up with 0.11 times 660 times 10 to the power of negative 9 divided by 2 divided by 0.12 and divided by 10 to the power of negative 3. So I end up with, that would be a delta x of 3. Looks like I have to do 3.0 because we have two significant digits here, because there's 2 here, 2 here, and 2 here, times 10 to the negative 4. This will be in meters. Sometimes you would write this as delta x equals 0.30 millimeters. That's my distance between the slits. So let's look at another problem. Here we have an air wedge that is 9.8 centimeters long. It's separated at one end by a piece of paper that is 0.019 millimeters thick. The distance between the centers of the first and eighth successive dark bands is 1.23 centimeters. What is the wavelength of the light being used? And this is a way that if you go to a physics light lab or a physics lab that has these air wedges, the distance between those slits is sometimes on the order of tenths of millimeters. So what they sometimes do is they'll measure the distance across all of the bands, and then they'll just divide it by how many bands there are, or not exactly how many bands there are, but how many bands there are minus 1. This will give us the delta x, and you kind of see that that's shown there, but I will show you how to do this on the paper here. So the information that we're given is that it is 1.23 centimeters between the first and eighth dark bands. So between the first and the eighth, we will end up having 7 delta x's, because we have, this is our first band, here's our second band, we're counting the gaps. So there's 1 gap between here. So of all the gaps, we'll have 7 gaps. That means that 1.23 centimeters is equal to 7 delta x's. So the delta x value is 1.23 centimeters over 7. And I'll just not evaluate this, but that's going to be my delta x. I'm going to substitute that in for my delta x. So I'm using this equation again. I'll start here. Delta x equals L lambda 2 over t. And what I'm asked is, what's the wavelength of the light? So I have to rearrange this for lambda. So lambda equals 2 delta x t over L. Lambda equals 2. Delta x is 1.23 centimeters times 10 to the negative 2 over 7. And the thickness was 0.019 millimeters. This entire thing over my L, which is 9.8 centimeters. So 9.8 times 10 to the negative 2 for centimeters. So I'll substitute all of these values in and solve. 2 times 1.23 times 10 to the power of negative 2 divided by 7 times 0.019 times 10 to the power of negative 3 divided by 9.8 divided by 10 to the power of negative 2. Now, because we're looking for a lambda, what we should end up with is something on the order of the hundreds of nanometers. So I have 6.81, and I should round this to two significant digits, so I'm going to write lambda equals 680 nanometers. Okay, moving on, here's another application of air wedges. If we're measuring the thickness of a hair, we could put a hair between an air wedge, and it'd basically be the same thing. There's other things that are measured here. Sometimes they're thicknesses of insects, very small insects like fleas, and I can't think of anything else right now, but hairs, papers, and insects are things that are measured with air wedges. So in this case, light shines on this, and with that 600 nanometers, it says the light intensity is 0 at the point of contact of the two plates, followed by 9 alternating bright and dark fringes. So we have bright, dark fringes. So in this case, we don't have our L. So this is the more difficult type of air wedge problem. It's still solvable. You just have to think about this a little bit more. The trick is, and here they give you the hint, but the trick is if we don't have our L, we would look into the question to see if they tell us how many fringes we have. And in this case, they're telling us there's 9 sets of bright and dark fringes. So that means that every time we have a bright and a dark fringe, our L increases by a distance of delta x. So if we have 9 alternating bright and dark fringes, our L is 9 delta x long. So using that information, I know it's given to you as a hint here, sometimes it will not be. We can try to solve this problem. Let me clear this out, and we're starting with this equation here. Delta x equals L lambda 2 over t, and we're asked to find the thickness t. So to rearrange this, I end up with 2 t equals L lambda 2 over delta x. Now, one thing you might notice is you weren't given the delta x value here. So a hint is, if you're not given the delta x and you're going to need it to solve, try to write your L in terms of delta x. So what we do, L is 9 delta x. Lambda, this light was 600 nanometers. 2 delta x. The delta x in the numerator and the denominator will divide and give us a 1. So this becomes, I'll just write it without the delta x's, 9 over 2 times 600 times 10 to the negative 9. So putting this in the calculator, 9 divided by 2 times 600 times 10 to the power of negative 9 gets me to 2.7 times 10 to the negative 6. So I have to treat the 600 as two significant digits because that's what we do in this course. That's our minimum. So 2.7 times 10 to the negative 6 meters is my thickness of the human hair.